Right, everyone, welcome back. I hope you enjoyed the lunch break and used the opportunity for good discussions and a bit of networking. One comment before I start introducing our speakers. There are some posters. Maybe you already visited them during the break. Otherwise, in the coffee breaks, you still have opportunities to check out the great posters that people brought. All right, so my name is Lauri. I will be sharing this session, which will be an AI deep dive session. And I'm very excited to present our first speaker, who is Naoki Kiyohara. He is a third-year PhD student in the Department of Computing here at Imperial, supervised by In-Chen Lee. And he will be talking about neurostochastic flows. And with this, please give a round of applause for our first speaker.
Thank you. Hello, I'm Naoki Kiyohara, third-year PhD student from Imperial and researcher in Canon. And today, I'd like to talk about our work titled Neurostochastic Flows, Solver-Free Modeling and Inference for SDE Solutions. Okay, let's start with background. Stochastic differential equations, SDEs, are ubiquitous. For example, in finance, it underpins the models for in finance in the stock price and the for physics for some particle systems with stochastic dynamics, and for modern machine learning, specifically like a diffusion models. There is a underlying SDEs used to model. And for specifically for SDEs, Ito SDEs, it consists of two terms. One is a drift term, which is a deterministic term like a ODE. And the second term is a diffusion term, which comes from the Brownian motion, which is stochastic. In machine learning, the common way to model the SDE directly from the data is done by the modeling this drift and diffusion term by neural networks, and then using some solvers like a Euler-Maruyama solvers, we discretize with respect to time and do recursive update over the state. However, there is a computational challenges of neural SDEs because each step requires a previous step, which means we need to do it recursive computation. And as a result, for the computational complexity scales linearly to the horizon length, like this. It requires recursive computation, and if we want to make it more accurate, we have to make the delta t very small, and we have to compute parallelly with recursion. And as I said, this is very costly for long horizons. And so what we tried is to conquer this problem by changing the viewpoint of modeling it. Here is the main idea that shifts viewpoint from strong solution to weak solution of the SDEs. In the SDEs, there is two types of solutions. One is a strong solution, which defines each path, briefly speaking. For more concretely, the strong solution is a solution defined on a given probability space with a given Brownian motion, which means that we first fix the Brownian motion, then we get the exact path given this Brownian motion. The neural SDE models using this idea because we fix the random seed first and generate new random variables for each time step, and it generates each pass. But there is another kind of solution, which is a weak solution. Weak solution is defined on the as a probability distribution, which means that we can, if we, for example, like if we model the transition kernel of the SDs, we can have the sample of each time step without having the exact paths, right? The more exact definition of the weak solution is a solution where the probability space and the Brownian motion are part of what you can choose, and you only require that X and some Brownian motion satisfies the SE and the correct distribution. And our idea is the latter one, which means we model the Markov kernel characterized by the transition law, which is the form of the conditional distribution, instead of directly modeling the drift term and diffusion term. Yeah, this is the illustration of our idea. Instead of having the exact path, we get the conditional distribution conditioned on the initial state. Then if we model this conditional distribution, then we can have a sample for arbitrary time, yeah, with conditioning additionally on the delta t, and yeah. But just simply modeling this conditional distribution using the neural networks is not enough, because we have to satisfy all of the properties that SD's weak solutions fulfills. There's 4 properties. First one is independence, which means if we have a non-overlapping intervals, each transition kernels are independent. The second one is identity, which is very simple, because if the time duration is 0 gap, then the state should be the identity. And the third one is a flow property. This means that, yeah, if we integrate the SD from the A to C, this should be the same as A to C via intermediate time B. So this is naturally fulfilled if we model if we model using the drift term and diffusion term. But in our case, we model the conditional distribution directly, so we have to fulfill this. Yeah. And finally, this is only for the autonomous SDs, which means that the drift term and diffusion term doesn't depend on the absolute time t. And in this case, there is this stationarity property, which means that this conditional distribution doesn't depend on the absolute time of each starting point. The first independence property is easily fulfilled by just sampling without having overlapping, because we model when we model this P, we use every time we use a fresh random variable, which means that each interval is the independent. But the problem is the other 3. To realize to fulfill such properties, we designed the architecture for this model using the conditional normalizing flow, specifically the conditional affine coupling. This consists of two phases. One is the base distribution, which is Gaussian, and the later one is transformation using the conditional affine coupling. The first one, we have a conditioning on the initial state and time gap and the absolute time for the non-autonomous case. And the interesting point is that we model with how to say, so that when delta t is 0, it can be the identity. If you look at this equation, you can see that if the delta t goes to 0, then this is just like an identity map, right? And so for later conditional affine coupling layers, we also have a delta t scaling as well as a base distribution, so that it goes to identity when delta t goes to 0. Now, this is the more, how to say, computation, has visualized computational graph for that. And the black part is a conventional affine coupling structure. And the red part is what we added. Yeah, as I said before, when delta t is 0, everything is identity now. And using this architecture, it is guaranteed that when the time gap is 0, this is identity. And also, it is very easy to guarantee the stationary when we drop this absolute time from any conditioning parameters. Okay, now 3 of all properties is guaranteed by its constitution. However, the most challenging part is a flow property. Flow property, again, is that the consistency between one-step jump and two-step jumps. And if we sample one step and if we sample two steps, this distribution must match if this is a solution of the weak solution of the SDE. But it is not guaranteed because we model this transition directly using neural network. So we have to match these distributions. To assist it both distribution matches, we introduce discrepancy between one-step and two-step distributions. However, the challenges in this computing this discrepancy, which we call flow loss, is that the marginalization is generally intractable for this two-step one. So we cannot get the direct access to the marginalized density. And instead we can think of doing the naive Monte Carlo estimation, but it would require many samples. So instead, we derived the upper bound for the Kayal divergence between one-step and two-step transition. Yes. And here is the upper bound for the one-step to two-step Kayal divergence and two-step to one-step Kayal divergence. And both contains the auxiliary model. And this is a form of the bridge distribution. And this bridge distribution means that this is the meaning of this is the distribution of the intermediate state given the initial and last state. And interestingly, both upper bounds contains the same form of this auxiliary bridge model. So if we combine these two upper bounds terms as a and introduce it as a regularization term with regularization term, we can just update this bridge distribution model and the neurostochastic flow model P jointly, and both terms assist each other because because it shares the same model for the both direction of the Kayal divergence. And finally, we get this. We can fulfill all of these properties of this transition kernel. So now the training objective is simply negative log likelihood plus the flow loss. Because we use the normalizing floor architecture, it is tractable to get the negative log likelihood, and this is very stable training. Next, let me show you the experimental thing. Firstly, we have done this experiment using the stochastic Lorentz attractor. Stochastic Lorentz attractor SD formation is like this. This is quite simple. For each dimension, it is linear. It consists only on the linear terms. However, interestingly, this outcome is chaotic. So this is an interesting example. So we use this. We compared two models using our model and neural SD models. And this is the trajectory visualization and this Kayal divergence and computational cost. If you look at these trajectories, I think you can see that our models really fit with the ground truth, and but existing neural SD methods, however, is a bit off from this ground truth. And actually, it is also in this, we can see in this Kayal divergence for each time point. For every time point, our neurostochastic flow showed a lowest Kayal divergence between this prediction and the ground truth. And interestingly, in terms of the computational cost, we have the same and lowest computational cost for every time point, even though we use comparable network size. Yeah. And this, however, it is sometimes difficult to apply to the real-world data because sometimes some of the dimension is lagged, is partially observed. And sometimes it's a high dimensional. Even though we can just use this SE on this high dimensional data directory, it is sometimes convenient if we have the smaller representation of the dynamics. Latent SEs are a powerful solution for that, but again, it requires a high computational cost for the latent part. So we replace SDEs with neural stochastic flows. And this is the comparison between the representative regular grid model, discrete model, and our latent NSF. And variational space model, which is a very common workaround for this for the regular time grid model used for like RLs, like in Planet or Dreamer. But the problem is that this is only for this. It's only for the regular grid one, and our model have access to this closed form log density, so we can easily fit to this to VSSM just by replacing this latent model to NSF. And we did the experiment on this motion capture real world data and the stochastic moving MNIST data set for the validation for the high dimensional data. And we observed that for both one, specifically for CMU motion capture one, we get the best or tied best performance, and the speed is 2 orders of magnitude faster. And for stochastic moving MNIST problem, the performance is comparable, while ours is 2 times faster. Yeah. Okay. Yes, there is some work related to us, but ours is the only one that can model general E2 SDEs, and we can do the solver-free and solver-free training and inference. Okay, maybe that's it. And our key benefit is one-step prediction for arbitrary time gaps, and speed is up to 2 orders of magnitude faster, and the stable training is realized. Okay, thank you so much.
Thank you, Naoki, for this very interesting talk. Are there any questions for our speaker? That's not the case yet. Then I will start with one. Sorry. Yes, please. No, you can
Yeah, thanks. Very nice. I was wondering, why do you need the underlying SDE, to have it in a continuous form? I think this is applicable to a discrete setting as well, right? Some kind of an iterated function system kind of thing.
I see. The motivation why we use this continuous time model is that to have the continuous representation of the physical dynamics. Actually, this work is objective to use as in model-based reinforcement learning. And in the case of model-based reinforcement learning, we have to have the model for this physical world, and the physical world is based on this on the differential equations. So then we thought to model the using the continuous time model, and I think it can broaden the way of, for example, like usual RL case we only use this discrete time, regular grid action, right? But we can extend this to variable length action scales to deal longer task with a shorter step of inference. Yeah.
Thanks. I'm wondering, can you just say a bit more about how the Kayal bound, the Kayal divergence bound changes with the time gap? The Kayal divergence bound, how that changes with the time gap exactly? Because you would expect sort of the longer the time gap, the worse the approximation gets, right? So in terms of the relative length scale of the process, how it depends on the time gap? Thanks.
Actually, the dependency on the time gap is completely depends on this the outcome of the neural network, because it is a part the neural network for both a Bayes distribution and the Bayes distribution and the affine coupling layer learns. So even though you can see that this seems to be like a OLM-RM form, it doesn't mean that this is only for the small time gap. It is if the flow loss term is computed via long time range, you can just use the same time length. And yeah, is that what you?
What I was expecting.
Sorry?
I see that, yes, it's part of the sort of neural network here, but so then if I'm predicting things for longer time gaps, then this is where that goes in, right? So can you help me understand how that would translate to sort of worse performance? Because your flow consistency will not be maintained, right? Is the thought here. The intuition is the longer the time gap, the less likely you are to maintain flow consistency. Or is that
yes,
not true
in terms of consistency, not long. If the time gap is, if the time gap is not contained in the training data set, it means that it's a bit off from this the underlying SEs. But if there is a time gap in the training data set, it means that time gap is already learned. So it means that it can realize a smaller error, I believe. Yeah.
All right. Unfortunately, we have to cut the discussion short here due to time reasons. But let's thank Naoki again for this interesting talk. And while we set up, I will introduce our second speaker in the session, who is Lauri Laatu. He's currently a postdoctoral researcher here at Imperial as well in the Department of High Energy Physics. Previously, he did his PhD in Marseille, and he also worked at CERN at the LHC Atlas experiment. So exactly, his talk will be on sub-microsecond transformers for jet tagging. I'm sure you're all quite curious to learn more about this. So let's give a warm round of applause also for Lauri.
Okay, hello everyone. Yeah, our work is about sub-microsecond transformers for jet tagging on FPGAs. So the context is the Large Hadron Collider at CERN. CERN is the largest physics lab in the world, located next to Geneva, and Large Hadron Collider is the largest particle accelerator in the world. So we can see here in the picture, we have the city of Geneva, and this huge ring here is the Large Hadron Collider. It is 100 meters underground. It studies the elementary particles and their interactions, and you might have heard about the discovery of Higgs boson in 2012. So, Large Hadron Collider is a 27-kilometer long particle accelerator with two counter-rotating beams. So we have one set of beam going clockwise and one anti-clockwise. And we're colliding protons, and these protons are bunched up, and a bunch of protons is colliding every 25 nanoseconds. So that gives us a 40 megahertz collision frequency. And the collisions happen at the interaction points. So at each of these 4 interaction points, we have one big experiment. We are working for the compact muon solenoid experiment. It has this layered design. So here in the very middle, we have a very small interaction point. The detector itself is huge. So you can see here the small human for scale. So we have a layered design. Each of the layers are designed to detect the properties of different particles. So very first we have a tracking system, followed by calorimeters, and then finally a muon system. So the collision rate is 40 megahertz, but interesting physics events are exceedingly rare. For example, the Higgs boson is only found in 1 billion events. There's also no direct way to measure these rare particles, because they have an extremely short lifetime. So by the time we can detect anything, they have decayed to more stable particles. Those are the ones that are then measured with the detector. So because the interesting events are rare and we cannot store everything on a disk, we need what we call a trigger system, which is a two-staged one. We have event selection at low granularity at 40 megahertz, called the level 1 trigger. And this one then, these interesting looking events are then fed to the high level trigger to select what is actually then stored on the disk. And a bit more about the challenge of the data processing. So LHC datasets are huge. In this plot, we can see the latency requirement and streaming data rate. The LHC level 1 trigger is here, the high level trigger here, and for reference, Google Cloud is here. So we have more data than Google Cloud at the year of this making of this plot, which is a couple of years old. Interestingly, also we have two squares. One of them denotes what we can do data latency and data streaming rates with CPUs and GPUs, and when we do need to have more programmable logic or application-specific ICs. So that's the level 1 trigger territory there. So also as a reference, every 4 hours, 1 exabyte of data. So the data volumes are huge. And the LHC has been running for almost 2 decades, and it has been running quite well. But in the future, we are looking to do more precise measurements and searches for new physics. So we need a increased collision rate. So per bunch, there will be more particle interactions. So this will require huge detector and electronics upgrades, but also introduce a noisy environment. So we need more advanced algorithms. That's where machine learning comes into play. So one of the tasks that needs to be done real time is called jet tagging, which is the process of identifying the type of particle that initiates a jet. So in this plot, we can see an illustration of an event, 2 colliding bunches of protons here in blue, resulting in the outgoing particles in orange that are then measured and reconstructed. Here seen on the cylindrical coordinate plane, and the size is the energy that was measured. So this can be represented as a set of particles where each particle has its cylindrical coordinates and its energy, and the ordering doesn't matter. And out of this, we have to then determine what was the originating particle that gave this kind of splash pattern, let's say. And the latency requirement is quite extreme. For jet tagging in the level 1 trigger, we are looking to do about 100 nanoseconds for this full computation. The dataset that we're using is a simulated dataset that is quite commonly used in these fast machine learning benchmarks. And it contains up to 150 particles, out of which we are maximally taking 64 most high energetic. Attention for jet tagging has been done previously, but for online mostly. So we have a model called particle transformer, which is the state-of-the-art model for offline. It is huge, and we are in no way able to run that in real time, so we have to do something else. There's also previous transformer implementations also, but they are doing more simplistic data and not getting into the sub-microsecond latency requirement. And here on these plots, we can see what attention does in jet tagging. So here we see again this plane of particles that were measured and their attention maps, attention correlations, and here the attention map. So the attention is able to capture these particle-to-particle correlations. So the models that we have in these studies are, we have 2 different attention models. One of them is a regular multi-head attention. And the second one is what is called a linformer. It is a way to linearize the attention. I'll show you next slide how we do it, because there was also another linear attention, but it's a bit different. Then we're comparing it to a deep set, which is a common model to do this task with. And also already being deployed at the LHC. So it's interesting to see how it performs against that. And these models are quite similar in architecture, but the attention models are here introducing the attention layer, which allows for particle-to-particle message passing, which the deep set doesn't have. So a bit more about the attention types that we're using. Both of them are based on the scale dot product attention. Has two matrix multiplications and a softmax. The difference in the attention comes in the Lin former is that the key and value are projected in the lower dimension before it goes into the scale dot product attention, which gives us n times k square, scaling as the input becomes longer, whereas the multi-head attention has n squared. And then we have to optimize these models for FPGAs. So FPGAs are programmable logic, which are able to use arbitrary bit widths. So we are not bound to, let's say, 32-bit floating point numbers or 8-bit integers. We can use arbitrary bit widths, anything above 1. And if you look at the weight distribution of a trained neural network, usually it looks like a Gaussian, where we have very few high magnitude weights. So we don't really need to represent big numbers at all. And as the computation is a weighted sum, the low magnitude weights are having very low contribution. So we can either prune them or represent them with lower precision. So we can use two key techniques: quantization of our training, QAT, in which we are training the neural network to perform with lower bit width weights. We can also do pruning, which results in sparse weight matrices. So in FPGAs, operations with zeros can be omitted totally, so we can reduce the amount of compute we need to do. And we are doing this with a method called high granularity quantization. It does these two optimizations, QAT and pruning, at the same time. And it does it with a loss-aware quantization. So we are learning optimal bit widths for every weight. And by allowing a virtual 0 bit width, we are also able to introduce pruning at the same time. And we're doing this with the framework called HGQ2, which results in per weight quantized neural network. And also data lanes can be per data lane quantized. And it does it by estimating an effective bit operation. So we can compute the bit widths, product of the bit widths, and summing them together while training. And that roughly corresponds to the amount of compute that we need in FPGAs. And then we control it with a parameter beta to control how big of a regularization for this bit width we want. And we don't control beta directly. Instead, in our application, we know how much compute we have because we have a set FPGA and we have set amount of resources on it. So we are instead setting a target of effective bit operations. And then we are using a technique from control engineering called PID control to then adjust the beta so that by the end we have a trained network that takes the desired amount of resources on the FPGA. So in these plots, we can see how the effective bit operations as a function of trained epoch goes quickly down. It's a log plot. And how the beta is adjusted to achieve that, and how the training and validation accuracy are evolving throughout the training. So the validation accuracy, while it would be the best within the first 100 epochs, that is way too large for our application. So we are getting highly sparse low bit widths here, which we can then actually deploy on our FPGA. Then doing this for attention requires special considerations because attention is slower to learn than the rest of the network. So what HGQ does tend to do is prune away the attention after which it doesn't do anything. So what we're doing is we are constraining the attention bit widths to at least 1 bit. So we can see in these plots the bit widths for the multi-head attention in this case and how many certain bit widths that you have in a network. We start with 12 and 13 bits. After 30 epochs, we have a reduced bit width, but after 500 epochs, it's mostly zeros. So it pruned away the layer, which we don't want. So what do we end up with bit widths? Is here you can see plots for linformer. We have the attention layer constrained to at least 1 bit, and the rest of the model. And different color is how many input particles we have. So we have a set area of the FPGA we can use. As you introduce more longer sequence to process, but you have a set amount of compute, the only way you can do it is by introduce higher sparsity. We can see that here, the shortest input at 8 particles and the highest input with 64. In high bit widths, they are almost matching, and the big difference comes with the high amount of sparsity that those then have. Further, when we deploy, we can use a technique called distributed arithmetic to turn our matrix operations to optimized adder trees. So CMVM optimization using distributed arithmetic. So we can split a multiplication into additions and bit shifts. We can see an example of that for 2 static coefficients, 3 and 11, where this is the resulting bit shift and adder tree that then results to our Y1. We just do it for the full weight matrices. And this further reduces the amount of compute that you need. So this is our full training flow. Initially trained with HGQ. Then we are using a tool called HLS for ML, which turns trained models into high-level synthesis language for FPGAs, in which this is integrated with DA for ML, takes in our CMVM problems and gives us instead optimized adder trees, and then we are synthesizing the network as a FPGA firmware. So for performance, the attention methods here with blue and orange, and we can see that the accuracy as a function of input length. Initially, multi-head attention and linformer are almost equally performant, but as the sequence length increases, our n-squared scaling multi-head attention starts to perform comparatively less and less well, whereas our linformer with the linearized attention is the best performing model here. In comparison to deep sets, we are at all input lengths performing better than the deep set. And the previous best in this data set was the MLP mixer architecture, which in the paper started 16 particles, but all of these, at all particle input lengths, we are having better performance. Then we have a per layer and not heterogeneous way of quantizing or quantization of our training called QKeras. And we have two deep sets, one with high granularity and one with per layer. And we can see that that one didn't perform as well as our HGQ trained deep set. So how much resources are we using on the FPGA is seen in this with the lookup table usage on the FPGA as a function of the particle input. We can see that we had set a fixed amount of resources we can use on the FPGA, and our networks in blue, orange, and green are in this ballpark region of having set amount of resources, whereas if you do per layer quantization, you start to use more and more resources as your input length increases. So as a conclusion, we can train high granular transformers with our tool. And as we can see, the multi-head attention does not scale well on the FPGA since it scales in n square as the input increases. The linearized attention from linformer can be is a better candidate for FPGA deployments. In HGQ, you get up to 2 orders of magnitude reduction in resources when you train your networks by using this effective bit operation that is minimized throughout the training. Next steps is more complex data set. This is a fairly simplified data set of what could happen as a jet tagging task, but it does not correspond to the real world conditions. So we are now moving into more complex data sets where we expect to see better improvements because the data gets noisier. And then this is now a jet level task. So we are having a focus area of the event, but we would like to do a full event level processing, which we're also working on right now. Thank you for your attention.
Thank you very much, Lauri. That leaves us with a lot of time for an interesting discussion. Are there any questions from the audience? I can start with one, and you can think about what you're interested in. I wondered about your results. I found it very interesting that the multi-head attention worked so much worse than the linformer. And I just wondered, do you think this is just due to the asymptotic complexity that you showed at the beginning of the talk, and it's basically just this, or is there anything specific about your FPGAs in the architecture that also makes the linformer perform so much better?
Not so much on the architecture, but the optimizations we can perform. So in the scale.product attention, we have two variable matrices that we cannot reduce these operations with the methods we have. Instead, we have these constant weight matrices that can be highly optimized, and the attention doing these two variable matrix operations that cannot be optimized as well. So that's the main reason it performs so much better.
All right, thank you. Are there any other questions? Oh, perfect.
Thank you very much for the nice talk. It's a very naive question, but your last point on, you said your next steps is for a more complex data set. What extra data do you think you would include, and how much improvement in performance do you think you'll get from this?
So we are now working on a more complex data set. I think the paper talks are out, paper coming soon. It is what we call a foundation model data set. So it contains full events for a lot of physics processes. So that's our target. And we expect, ultimately lower performance because the events are noisier, but better performance gap to other methods.
All right. Then maybe let me ask one final question. I was curious, at the beginning of your talk, you showed a very nice plot also about the current compute or streaming data and versus how much compute we have currently. And about that, I just wondered, you also mentioned that you have very good offline models at the moment, like particle nets, which is, I think, a GNN, and you showed this particle transformer as well. Do you think like hardware improvement is so fast that at some point it will be feasible to actually run these really high precision offline models soon? Or do you think we are very, very far from that still?
We're still quite far, but we are going towards that direction. So what we have now in the trigger is an FPGA or a board that is looking for specific event types. And we have several boards. What we could do is like a trigger foundation model. Instead of having one board per one event type, roughly, you could have the resources of all of these boards running one big model that would then do all of these as like a foundation model.
Very interesting. Thank you. I don't think I see any other questions, so let's thank both of our speakers again for this very interesting session.
Thank you.
And then now we have another coffee break, and we meet again here at 2:30.
Be strict but kind. So if you're getting to like the 1 minute left, I'll just do this. Okay. And if you see me stand up, try and make whatever you're saying the last thing.
Okay. I'll try to also keep it on my phone so that I can.
Thank you. Yeah. Are we ready? Okay.
The slides are.
Yes. Is there a clicker? Should be on that, yeah. So if you just click. Yeah, okay. Good. All right. Okay. Welcome back, everyone. I hope you had a chance to have a look at the posters and have a caffeine break. So next, for the next session, we have 5 more flash talks, so 10 minutes each. So just because I'm not sure who all our speakers are, I'm going to be sitting here, so if I give you a red sign, that means you have 1 minute left. But I hope you've all practiced the talk in 10 minutes, so I don't have to be mean. And so it's my pleasure to introduce our first speaker, Marta Aparicio Rodriguez from Imperial College London, who's going to be talking to us today about concept reachability in diffusion models.
Thanks. Yes, so I'm going to be presenting the work I did with my supervisors, Anastasia and Ksenia. And just to give a quick overview of diffusion models, which you'll probably know about. So we were working with images, and so in our case, diffusion models are generative models that learn to turn random noise into coherent images. And we do this through a reverse noising process. So we start with noise sampled from a standard Gaussian, and we, at each step, gradually denoise it. And this denoising is typically done with a neural network such as a UNet, which involves a downsampling set of blocks and an upsampling set of blocks connected by skip connections. And this unit, what it will do is at each step, it will predict the amount of noise in the noisy image and use that to get a slightly less noisy version of the image at the next step. And most of the models that we work with nowadays that we might be using to generate images also involve some kind of text conditioning. And this is usually inputted through a caption that gets passed through a text encoder, and then passed into the model through cross-attention layers that will ideally align the generation process with the semantic information in the caption. So even though we get very strong generation, even with the models that we have now, there are still cases in which generation fails. And an example of this is if you go to ChatGPT and ask it to generate a mouse chasing a cat, it tends to not be able to do so, and it will tend to generate the cat chasing the mouse instead. And this is likely because there is some bias, because we usually associate that the cat is the one chasing the mouse. And this is a bias that gets passed on to the trained data. And so the model struggles to do so, even though it's getting better. So this led us to consider 2 questions. Okay. Firstly, are there alternative methods to prompting that can allow us to generate the concepts that we're trying to generate? And secondly, what constraints in the data could be affecting this generation of the concepts or this reachability of the concepts? So for the first question, we looked at an alternative of steering vectors, and we did this in 2 spaces. So I'll just briefly mention the idea of what we're doing. So we could have, for example, that we have a prompt YS, and we use it to generate with our model an image XS. And XS might be slightly different from what we're trying to actually generate, which would be our X target. So the idea of the steering vector is that we're trying to optimize a vector V, such that when I add it during the generation process, it's going to guide or steer the generation towards the target that we're trying to generate. And we did this by adding these vectors in 2 places, one being the encoding of the text, which is known as the prompt space, and also in the bottleneck layer of the unit, which is known as the H space. So going back to our second question, we had 3 ways that we thought that the data could be constrained that we wanted to explore. And first one would be, okay, what happens if we have concepts in our data, but perhaps they are very rare or don't appear very often in our data? Secondly, what happens when maybe these concepts appear in our data, but they're not very well mentioned or specified in the captions? And finally, what happens when we have two concepts that consistently co-occur? So if one is in the data, the other one is also in the data, in the image, and so on. And what happens if I try to generate a concept combination that only contains one or the other? So what happens if I try to disentangle these two concepts? And to do this, we required to be able to control the concepts that were present in our data set. So we looked into just using asynthetic data. And what it involved was there would be two shapes in each of the images in our data set. One would be partially covered by the other, and it would be with different colors. And the captions of the data would just involve a description of the relation. So in the first image, for example, just a blue circle behind a red square. And going into how we analyze or define the concepts in these images. So what we did is we looked at the back color, back shape, front color, and front shape. And we denoted these concepts as C1, S1, C2, C2. C2, S2, and we just allowed the position of the images to vary to be able to generate a large amount of images to train our model on those. So going back to the three constraints that we were looking at, for scarcity of concepts, what we did was we started with our full data set that had every concept appearing an equal number of times and was completely balanced. And then we created versions of the data where we gradually removed the presence of one concept from the data set, trained our model on these different versions, and then evaluated how well we could reach concepts that contained that concept that we were removing. And for the second case, what we did was we started with our original data set that was mentioning all the captions, all the concepts that we were interested in. And then we created versions of the data where we removed the specification of certain concepts. So perhaps our captions would not mention the back color of the shape in the image. Finally, for tied concepts, we started with two concepts that were always seen together. And then we also tried to break this bias by introducing the presence of one of the concepts gradually into the data. And again, try to evaluate how well we could reach either of them separately. And the way that we evaluated this performance or this reachability was, okay, I have my trained model. I have my three methods to generate these images, so I would just use one of them. And then from there, we get a set of a large number of images that, in theory, should follow the target concepts that we're getting, that we want to generate. We use those to basically, with some classifiers, identify the concepts that are actually in the images. We compare it to the ones that we were trying to generate, and from there we get an accuracy score. So in terms of results, for scarcity of concepts, the first thing was that actually, in order to generate a moderately high number of images containing the rare concept, we don't need that many images. So we noticed that there was this threshold below which reachability dropped quite fast. But beyond this threshold, there was a relatively stable high level of reachability. Another thing that we noticed was that with certain cases, we found that prompting would have a very, very low accuracy, so almost zero in the case here. So this graphs, what they're showing is on the x-axis is the proportion of images in the data set containing that concept. So this would be the proportion of images containing square in the front. And we're trying to generate concept combinations that contains a square in the front. And what we found was that there were cases in which the reachability through prompting was very low, but with steering, with either method, we got a reachability that was closer to 50, 60%, which was quite significant. In terms of underspecification of concepts, firstly, we found that decreasing the specification in the captions rapidly decreased the reachability of the concept combinations, which perhaps for prompting was more expected, but was also reflected in steering in the prompt space and steering in the H space. And this, even though we did see some improvement with steering, was very clear when you go into just a specification of maybe 2 concepts, as is in the 3rd column from the left. Finally, for tied concepts, what we found was there were cases when the 2 concepts would be co-occurring all the time, and steering on the prompt space would easily bypass the accuracies that we were seeing just by prompting. So what this graph is showing here is an example where we have that blue in the back and circle in the back are seen consistently together. And the horizontal axis is showing the reachability to only blue in the back, so not a circle. And the vertical axis is showing the reachability to only a circle in the back. What we do is we increase the proportion of images containing only blue in the back. So as expected, the reachability to only blue, which is on the horizontal axis, increases. But what we saw was that there was also some kind of, with some variability, increase in the reachability to the other concepts that was not seen. So somehow the model was being able to understand better what the other concept was by seeing more of the one that we were introducing. Okay, so just as final conclusions, overall we found cases in which there was a significant improvement in reachability through steering, which somehow is suggesting that the model is capable of generating the concepts that we were trying to reach, but perhaps prompting is not the best outcome. So maybe in this cross-attention layers, the association between the visual image and the semantic information in the captions is not being fully connected. Secondly, we found that there were differences in reachability through either space, H space, and prompt space. So somehow that is suggesting that perhaps there's certain areas in the network where we can access better reaching concepts than others. So that's also something to investigate a bit further. We also found that specification of concepts was significantly important on reachability, and it mostly is interesting in the case of steering, where it's shaping the latent space in such a way where when you try to steer and the captions are mentioned in the data set, the reachability can be significantly higher than otherwise. And finally, we highlight the need to explore alternative methods beyond prompting for improving reachability and trying to avoid retraining our models from scratch if the training data is insufficient to generate concepts through prompting. And yeah, you can check out the paper with the QR code.
I think just in the interest of time, because we did run over by a couple of minutes, we'll save questions for Marta in the coffee break afterwards and jump straight into our next talk. Okay, so our next speaker is Guiomar, Pescador, Barrios.
This is working.
Okay, great. So Guiomar is going to give us a talk about adjusting model size in continual Gaussian processes.
So hello everyone. I'm excited to present this work on adjusting model size in online GPs. It's not okay. So this was published as HTML. It was done with my supervisors Sarah Filippi and Mark van der Velde. So some motivation to start. I'm sure you all seen headlines like this in the past years, where we've seen that the energy needed to train and deploy models has continuously increased, and well, there is a concern for the environmental and energy impact of these. So methods that can maximize the computational efficiency given a given budget are very needed. On the other hand, we know that current AI models cannot learn as we go along, so as they receive a stream of data. So these are the two things that motivated this work. So a little bit of the setting. The cost of the models is actually very related to their size, and this is very big usually due to the large amount of information that we have right now. And this model size is usually set and fixed before training. But it's very important to set it correctly, because if it's too small, our model is going to underperform. And if it's too big, then we're going to waste computation. A model size can be, for example, the number of neurons in a neural network. In continual learning, we see the setting that I've talked about where we receive the data in batches, like in the picture. This becomes even harder because we receive the data in batches, it means that we don't see the full data set at once, so we cannot do, for example, cross-validation to set this hyperparameter. So ideally, what we want is the smallest model that gives us near-exact performance, right? So the question becomes, how big is big enough? And so this paper proposed a method to adjust model size in this continual learning setting. So just before I go into the method, a little bit about the model. So we do it in Gaussian processes, in regression, continual learning in Gaussian processes is very well known, but most of the methods assume a fixed model size. Well, we model our label y by passing the data points to a function f and adding Gaussian noise, and we put a GP prior on f. In this case, we assume zero mean and a kernel with hyperparameters theta. These models have a very high cost of n cubed, n being the data point size, the number of data points. So we need an approximation. So we do a variational approximation, and in this case, it means that we're going to approximate the posterior distribution by a variational distribution QF. And in the particular case of GPs, this approximate posterior is defined through a set of inducing variables. This is a subset. So if you look at the image, it's easier to imagine. So we have our data points in orange, and we're going to define our whole function through the black dots. And this is going to reduce our cost massively to m. And so the problem is going to be that the placement and number of inducing points is going to determine how good our approximation is. And from an optimization point of view, what we do is that we minimize the Kayal divergence between the approximate and true posterior. But as I said, it's a bit more complicated than that because we are in the sequential setting. So our objective, we're going to have, I'm not going to explain it, but we're going to have an online version of it. You can look at the paper to learn about that. But just to recap, we're going to have batches of data coming at us at every time, like you see in the picture. And we're going to have to adjust the model size, which only looking at this new data and past summary of the previous batches. And yeah, that's going to be the question. Should we grow the model or not to keep our approximation exact? So what was our method? Actually, the idea was very simple at the beginning. When we are trying to minimize the Kayal divergence, what we are trying to do is maximize a lower bound to the log marginal likelihood. So that's the best we can do. And so we want to maximize the blue line that you see on the screen. So we'd say, OK, let's compute an upper bound and sandwich our log marginal likelihood, right? This is very common to do. And we will keep adding inducing points until the difference between the upper and lower bound is less than a threshold alpha. But how do we set alpha? I told you that we don't have access to the whole data set, so we don't know anything about how our data set is going to be. And it's difficult to set this as a single value because the scale of the log marginal likelihood depends on each data set characteristic. So we need to make alpha dynamic. And we do it by defining a baseline. This baseline is the gray line called a noise model that assumes no structure of the data, which means that our worst case scenario. And we're going to set alpha to be a fraction of the difference between the upper bound and this noise model. And intuitively, it means that we're going to keep adding inducing points until we have captured, let's say, 90% of the difference between my worst case scenario and, well, the upper bound, which is supposed to represent my best case, which is the log marginal likelihood, the middle line. So does it work? Well, in principle, if the method works, we needed to adjust to different scenarios where the capacity of the model requirements, the model size requirements are different. So here we have 3 data sets. In the first one, you can see how the data is ordered, and we can see a linear increase of the model size. In the second one, you see how the data is sparse. So we've seen a linear increase, but all of a sudden it's going to plateau because the data becomes redundant, right? Whereas here we had new information all the time. And in the third one, you've seen that we only have data in a small, dense region, so we kept our model size very small until we have outliers. And so we grow our model size again. So as you can see, our method is capable to adapt the model size to different scenarios and keep the model size just as we need it, such that we don't sacrifice any accuracy. And just to convince you that model size is adapted, adaptive model size matters, here are two examples. On the left, we have 3 fixed size models, and you can see that as the batches progresses, only the one with m equals 30, it's able to match the exact GP, whereas our adaptive method is able to do it without any pre-tuning or knowing anything about the data. And on the right, we do the same thing for the training cost. And in this one, we have an oracle which knows the perfect model size at the end of training. But you can see that even if you leave the fixed model size from the beginning until the end, and instead of increasing it little by little, you're going to waste more computation. So just to conclude, we propose a stopping criterion for continual learning that enables adaptive model size. It doesn't require any predefined hyperparameters or any tuning, so it adapts to any dataset without having to see it in advance, and we showed that has a slower computational growth than other methods. This is important because it allows to have more efficiency within a given budget, which is, I said, it was one of the motivations that was given at the beginning. And in terms of future work, we've been extending this to more general models, and actually we're showing that this also has a lot of implications in batch learning, and I hope you'll get to see that work soon. Thank you.
Thank you very much, Guiomar. We have enough time for 1 or 2 questions, so sorry if you wouldn't mind.
Yeah.
What, for a minute more? Okay.
Thanks for the talk. I'm a bit stumped by seeing that the model size 30 doesn't perform as well as your model, even though it's like it's an over-parameterized model relative to yours.
No, actually, maybe I didn't know how I was in time. So actually, you see on the left, we have 3 model size, so M10, M20, and M30. M30 performs as good as the exact GP, and it's great. You could fix your model to have a model at 30 inducing points, but you can only know that this is the correct model size afterwards, because you don't see the whole data set from the beginning, right? Whereas our method is capable of just adjusting as we go. So that's what I wanted.
Yeah, got it. Yeah.
Yeah?
Maybe I just misread the
No,
Sorry.
yeah.
Thanks. That clarifies it. Thanks.
Okay, I'm going to do one more. I saw this hand up first, so I will try and be diplomatic.
Thanks for the talk. You showed in one plot that the performance reaches a plateau, and then you said that the data becomes redundant. Of course, that makes sense. It's the natural conclusion that anybody could take, and we'll agree on that. But I was wondering if it's possible to provide a theoretical warranty of that, maybe based on some information theoretic results. So for example, when you add more data, the fission information should improve at some point?
Yeah, so if you read the paper, actually, a bit of the intuition behind how we chose our stopping criterion was behind the minimum description length of the elbow. So we know that the elbow is going to encode how many bits we need to encode the number, write the bits that we need on any information. And so defining that baseline and then that optimal value allow us to somehow characterize how much we've learned. So that's, yeah.
Thanks.
Okay, thank you very much. We're going to move on to our next speaker. which is Jan, Orla, Ernst. So I should say also, as we're setting up, please do find the speakers afterwards, because I know there were more questions just then, and for our first speaker, we didn't have a chance to do questions, so please find them after in the coffee break. Okay, so we're all ready. So yes, I'd like to introduce Jan Orla Ernst from University of Oxford, who's going to be talking to us today on reinforcement learning for quantum control under physical constraints.
Hey everyone, so I'm going to talk about reinforcement learning applied to quantum control with physical constraints, and this work was a collaboration with Annika Chatterjee, Tim Franzmai, and Axel Kuhn, all from the University of Oxford. So maybe this is an important slide for everyone here, because maybe a lot of you are not so familiar with what quantum control even is in the first place. So quantum control is concerned with controlling the time evolution of a quantum system and perhaps steering it into some desired final target state. And quantum systems generally form the building blocks of nature, and controlling this is important in quantum sensing, quantum chemistry, condensed matter physics, and in particularly very important for building quantum computers. And here you can see IBM's superconducting quantum processor, which is also the architecture pursued by Google. And you can see some examples of experiments for atomic quantum computing. This one is from my own lab, and this one is from a neighboring lab in Oxford. So I'm going to quickly go through some theory that just formalizes the problem I'm trying to solve here. So in general, you have a quantum state which is described by a density matrix rho. And under something called the master equation, you can evolve the system in time using coherent control terms as well as considering these incoherent decay terms. And you get some final density matrix at a final time step. And then what you care about is the overlap of your evolved density matrix with some desired target. And the way you realize this is typically by imposing some time-dependent control actions A, and these can be microwave signals or optical signals. And the problem is then phrased in this sort of standard reinforcement learning fashion, where you're trying to learn a policy that maximizes the expected cumulative rewards, which usually contains some kind of fidelity contribution, because this is a thing that physicists actually care about. And in this setting, we also focus on the continuous bandit setting, because in general, if you have an analog system, your signals are continuous in time, and you can't just phrase this as a discrete problem. So two of the real innovations in this work, which was published at ICML this year, were that we formulate this physically motivated reward function. So first of all, you have a term here that penalizes overly large signal areas. And that is motivated in the fact that you don't have an unlimited amount of laser power or microwave power available in your experiments. And you might also want to find solutions which are faster in time, because that's something relevant for scaling up like clock cycles in a quantum computer. The other two things we impose are these signal smoothing constraints. So omega is some amplitude in time, and delta is some sort of time-dependent frequency. And we want to find solutions that have some kind of smoothness. And the reason is that, again, the electronics you have in the lab has limited instantaneous bandwidth. You can't just find these solutions and simulations which have instantaneous bandwidths of several gigahertz, but no electronics in the world is going to produce that signal for you in the lab. And then finally, there's also a contribution that is proportional to this logarithmic fidelity, because you want a fidelity that approaches 1 as closely as possible. And the other constraint we impose is a maximum numerical solver step size constraint. So the experiments I'm going to show are based on these numerical simulations where we solve the master equation. And this is sort of physically motivated in something we know about the time dynamics of the kind of solutions that we think are generally good in solving these problems. And they're generally not too fast. And the more solver steps you need, generally, in physics, we kind of know that you're probably veering away from what we think is an optimal solution. And then imposing this numerical solver step constraint generally really improves computational scalability, as you can see here. So you can be in a regime here, for example, where you impose some limit on the maximum solver steps, and you get a better solution, as indicated by sort of a higher fidelity. And you can also get there in shorter time, which is generally what you care about if you're trying to solve these problems practically. When it comes to implementation, two things that are really instrumental for making this work. We're using the Google JAX package with support for vectorization on GPUs, as well as a package called Qiskit Dynamics, which was built by IBM. And these really allowed us to scale this super well without doing too much software engineering. And I think this is a really interesting plot because regardless of what area you're working on, just when it comes to solving problems in reinforcement learning, I think this is extremely interesting because the first thing you see, PPO is the best algorithm for solving this particular quantum control problem, which maybe isn't that surprising. But the interesting thing here is that we measure the kind of quality of our solutions using the fidelity. And you can see that these vanilla algorithms, they contain a reward function which is just proportional to fidelity. But actually, when you look at how they learn over time, they learn pretty badly. And you would need a huge number of update steps to get any kind of good solution. And maybe you would never get there because the action space is so incredibly high dimensional. But when we use this kind of constraint formulation where the step size solver constraint and the smoothing constraints, you actually get much better solutions as measured by the fidelity, even though your reward function isn't just proportional to fidelity, which maybe is a little bit counterintuitive, but it's sort of a very interesting observation here. And you can also check out the software implementation on GitHub. It's fully open source if you want to try this out for some other environment. Now, when it comes to benchmarking, I mean, maybe some of this is not so interesting if you're not so familiar with the physics literature. But we do find that on 3 experimentally relevant problems with different environments, we achieve state-of-the-art results. In particular, you can compare results to more traditional control theory approaches, physics-informed neural networks, and other kinds of reinforcement learning approaches in this table. And ours is at the bottom in bold. And we also achieve more than 99.9% fidelity in all these systems. And that's particularly relevant because this is a threshold you need to surpass to do error correction for practical quantum computing. So the fact that we are above this threshold with our method is really good. And we also achieve really good robustness to noise. And this is kind of by design because we can train this RL algorithm on really big batches with different randomly sampled noise levels. So we can learn policies that are really robust in the face of moderate random noise. And when we have really strong biased noise, we can do something called multi-step sampling of the noise. And then we can also get much better robustness to this stronger biased noise because we sample the noise in time and then can sort of feed forward our optimal solution with the sampled noise. And for one particular experiment, namely this transmon reset problem, we are really confident that we achieve a much better result with very realistic parameters and simulation than what they achieved in the experiment by really trying to closely simulate this experiment. And my collaborator is closely working on actually verifying that this is indeed the case in a real experiment because these results are based on simulations. Another thing that we found actually really nice about these results is that often when you have solutions that come from a more complicated machine learning approach, is that you show them to an experimental physicist and they rip their hair out because the way the kind of signals look in time, they look impossible to ever actually generate. But one thing we found is that actually they have a fairly nice parameterization and they don't look too crazy. And especially for this solution over here, we can actually analytically fit a function to the kind of time-dependent pulse that we discovered with reinforcement learning, which allows for pretty easy experimental calibration. So there's only a few hyperparameters that fully describe this time-dependent amplitude and frequency evolution, which should allow for a very easy experimental calibration just by sweeping some of these parameters. And likewise, in this particular problem, we also find a solution I think that's actually fairly interpretable in terms of the physics that describes why this is the optimal time-dependent evolution of the controls. So just going to provide a little outlook of what we're working on continually and perhaps what we're working towards here. So one of my collaborators is working on experimental validation of these simulations. And towards the end of my PhD, I also worked on some device sampling and training. And I think this is quite challenging because, at least for the experiments that I worked on, you have a lot of shot noise, which means you need like huge batches. And if you only have one experiment, you can't do the same thing you do on a GPU. You can't just batch your samples by duplicating your experiment. And you also often have timing delays from the GPU to your control system and quantum device. So this is still work in progress, but there's some nice papers which attack this, which I think provide practical solutions. And with that, I just want to give a shout out to my collaborators who are really amazing. So Tim now works at DeepMind. Annika is still working on this stuff and is a really gifted researcher. And also big thanks to my PhD supervisor, Axel Kuhn. And please reach out if you have any questions or want to get in touch. Thank you.
Okay, thank you very much, Jan. Almost 10 minutes to the dot, so very good. We have time for maybe 1 or 2 questions. If not, then I can start with one. So you had this like reward function from the reinforcement learning with several different contributions. How are the weights looking like in this?
So the weights, that's a great question. So in general, like we did a lot of ablations that you can look at in the paper, but in general, this was weighted the strongest because this is ultimately the thing that you care about. And then these weights were sort of an order of magnitude lower. But they still provided like a really important component in improving the learning dynamics, even though they were much smaller.
And is this something you'd need a lot of fine-tuning to in task-dependent problems?
There is definitely some fine-tuning you need to do. Like it is hyperparameter sensitive. But I think in the ablations it showed that it wasn't like too bad. It wasn't like there was only one tiny like regime in the hyperparameter space where you achieved good convergence.
Okay, nice. Thank you. Any more questions? In which case, we'll move on to our next speaker. So thank you very much. And the next speaker is Aya Kayal. Okay, so our next speaker is Aya Kayal from the University College London. And she will be talking to us today about Bayesian optimization from human feedback near optimal regret bounds. I think we're ready to go.
Hello everyone, I'm Aya. I just finished my PhD from UCL, and I will be presenting today this work which was published at ICML, Bayesian optimization from human feedback near optimal regret bounds. It's a joint work between UCL and MediaTek Research, with Sattar Vakili, Laura Toni, Dashan Shiu, and Alberto Bernacchia. So let's start by the core motivation of this work. So we are often asked by ChatGPT which response do we prefer between response 1 and 2. And actually, studies have shown that humans are often much more reliable at providing relative preferences rather than absolute scores. So we find it easier and more intuitive to say that response 1 is better than response 2 rather than scaling each response on a scale. So there is an exciting line of research learning from these human preferences. But the problem is that human feedback is expensive. And this brings us to the key research question, which we are trying to address in this work. How can we efficiently learn using as little preferential feedback as possible? So we studied this Bayesian optimization from human feedback framework, and I'll walk you through an example in the context of prompt optimization to understand the framework. So at each iteration, the learner would pick 2 actions, xt and x prime t, corresponding to 2 prompts in this example. And then we would ask the human which one they prefer, the response of prompt xt or the response of prompt x prime t. And then we would observe the binary feedback given by the human yt, and it's modeled as a Bernoulli random variable of parameter mu of h, where mu here is a link function, let's say it's the sigmoid, and h is the unknown preference function which we are trying to estimate. And it's simply the difference between the unobserved utility function f of xt minus f of x prime t. And the third step would be to update the model and evaluate the regret. The regret here is a form of suboptimality gap between the pair of actions that we have chosen, xt and x prime t, and x star, which is the best action that could have been chosen retrospectively. And then this loop is repeated again and again until converging to the user's most preferred action, so the most preferred prompt, x star in this example. But we want to find the best prompt while minimizing the number of human queries. That's the goal of the work. Another example could be a restaurant recommendation, which can also be formalized as a BOHF framework. So instead of picking 2 prompts at each iteration, we would pick 2 restaurants and then ask the human which restaurant do they prefer, evaluate the regret, and then do that again and again until finding the best restaurant to recommend to this user. So the main contribution of this work is that we propose a novel algorithm called MRLPF, multi-round learning from preference feedback. And this algorithm efficiently solves this BOHF framework. So it finds the near optimal action while minimizing the human feedback. And we analyze theoretically this algorithm and show that it has an improved regret bound over prior methods in the literature. So actually, prior methods, their regret bounds, they scale with a large constant kappa, which is related to the curvature of the link function. And the regret bounds also scale with gamma t, which is a complexity measure called maximum information gain. And this can render the regret bounds vacuous in some cases. So, however, our algorithm enjoys a regret bound of the order big of square root gamma t, which is a sublinear regret bound, and it's considered a big theoretical improvement compared to prior works. We also validate this theoretical improvement through experiments on both real-world and synthetic data sets. So how do we estimate this preference function h? Since the problem resembles a classification-like problem because we're trying to model the preference of preferring item xt over x prime t, so we actually, h is the minimizer of this negative log likelihood loss, which is given here in the orange box. And yi here is the human feedback, which is either a 0 or 1, determining the preference of the human. Mu is the sigmoid function, h is the unknown preference function which we're trying to solve, and the last term here is the regularizer. And to solve this, we leverage the representer theorem, which gives us a parametric representation of h. So h can be written as a sum of these theta I coefficients and the kernel values at x and x prime. These are the training pair of actions observed. So if we replace this back into this negative log likelihood loss, we turn it into a standard optimization problem where we can solve it by gradient descent and find the parameters theta and eventually h. So here I'm just showing an example of the utility function f, which is, let's say, it's unknown, and h, the preference which we observe from the human feedback, and it's simply f of x minus f of x prime, and mu of h is just the probability of preferring x over x prime, shown here as a surface. We also estimate the uncertainty around our prediction of h by using kernel-ridge regression, which gives us a closed-form solution of the posterior variance, sigma star. And this is just the standard formula, but adapted to the preference-based case. Here Z is just the pair of actions, which we are trying to estimate the uncertainty at. And KT is the kernel values between Z and the training pairs. Big KT is the gram matrix. Lambda is just the regularization coefficient. And here kappa shows up in this preference-based scenario because it's related to the curvature of the sigmoid link function. Now, having introduced the key components of the algorithm, let's describe how the algorithm that we propose works. So our algorithm proceeds in rounds, And in each round R, what we do is that we select the pair of actions with the highest uncertainty in their preference. So this uncertainty, which I gave the formula in the previous slide, we just checked, we select XX prime according to argmax of this uncertainty. And then we ask the human which one do they prefer between X and X prime. And we repeat that again for a certain number of samples per round. And then what we do at the end of each round, we update our estimate of the preference function, both the mean of this preference function and the uncertainty around it, from the collected feedback which we collected during the round. And we also keep an action set that this action set keeps the action that are the most plausible actions. And what we do is that we refine this action set progressively. So at the end of each round, we check according to the upper confidence bound of our estimate of the preference function. If this inequation is satisfied, we keep the action in the action set because it's likely to be a good action, likely to be one of the optimal actions. And if not, we eliminate it from the set. So if we repeat this loop again and again with more rounds, this action set will shrink and we will converge to the user's most preferred action X star. And we also analyze theoretically the bound, the regret bound of our algorithm. And we show that compared to the prior methods in the literature, we achieve a square root gamma, where gamma is the maximum information gain, improvement over prior work. And we also eliminate the dependence on this kappa square, which is related to the curvature of the link function. So our regret bound is square root gamma t. And interestingly, it matches the regret bound of conventional BO with scalar feedback, despite that here we are using a much weaker feedback model, a preference-based feedback model. So this is saying that we basically need the same order in terms of preferences or scalar feedback to find the near optimal solution. We also validate this theoretical bound on the Yelp restaurant recommendation dataset, where we tested our algorithm in red, MRLPF, against Maxmin LCB, which is the most competitive baseline in the BOHF literature. And here we plot the regret versus the number of training time steps. And you can see that at the end, the algorithm in red does converge to a lower regret than Maxmin LCB. And this is also confirmed across other tested functions other than the Yelp restaurant recommendation dataset. We tested on some synthetic functions drawn from the RKHS of different kernels. So we tested with a square exponential kernel, Matern kernels with different smoothness. And we also tested on the ACLI, if the utility function is the ACLI optimization function. And consistently, we can see that our algorithm in red does converge to a lower regret than Maxmin LCB. Yes, and basically that's it. Thank you for your attention.
Okay, thank you very much, Aya. I think we have time for one very quick question before our last speaker.
So would these extend to worst-case bounds as well? Or do they talk about these worst-case bounds in this domain?
Yeah, this is the worst case.
This is worst case
yes.
too?
Yes.
Okay, thank you very much. And we're going to move on to our final speaker, Krzysztof Kacprzyk. Okay, so Krzysztof is going to give us a talk today on Skip the Equations, Learning Behavior of Personalized Dynamical Systems Directly from Data. Thank you very much.
Thank you. Yeah, thank you very much for inviting me to give this talk. My name is Krzysztof. Today I'm going to talk about our recent paper published at ICML this year. This is a joint work between me, Juliana Piskosz, and our supervisor, Michaela van der Schaar. So the topic of today's talk is about modeling dynamical systems, which are basically any dynamical systems that evolve over time. We see a lot of such examples in climate, weather, biological systems, ecological networks, but also things like pharmacology, disease progression, and financial systems. And in particular, we're interested in modeling dynamical systems in high-stakes settings, things like healthcare or pharmacology, where we usually don't want to use black box models. So we want to use models where we can actually understand the behavior and see what is happening. And the most common approach for modeling dynamical systems throughout the years have been ordinary differential equations or closed form ordinary differential equations, and they have been used in many things from epidemiology to tumor growth models to predator-prey modeling and so on. And there is actually an area of machine learning called symbolic regression, whose goal is to precisely discover these kinds of equations directly from data. And the way it would work is that we have our data set, which then we put into our equation discovery algorithm, and we get a system of differential equations that we're going to refer to as the syntactic or like symbolic representation of the whole system. But then the question is, okay, why do we need those equations? So we argue that in this work, the reason why those equations might be better than black box models is that we can perform some kind of mathematical analysis to learn about the system behavior, something that we call here semantic representation of the system. And that might mean different things. So that might be, for instance, what kind of shape the trajectory has, or maybe how different properties like maximum of the trajectory, the inflection points, the asymptote, how they depend on different parameters. So this kind of paradigm that we refer to two-step modeling of modeling dynamical systems, where we first discover an equation and then a human has to analyze this equation to kind of learn about this behavior. But there are some challenges with this approach, and one of them is this analysis is usually time-consuming, it requires expertise, and if you have equations which are very complicated, which may happen if you use an automatic way of discovering them, that might be even impossible. And the other important limitation is that if you now have those equations, perform this analysis, but now you see that something in the behavior is wrong. Maybe the trajectory has a different shape, maybe the property is not what you want. It's usually quite difficult to now go back to the equations and think what kind of terms to add to the equation, which parameters to change to actually alter the behavior. So in a previous iClear paper, we introduced something called direct semantic modeling, where the idea is to find a model which goes directly from data to the description of the model behavior. And in this work, we kind of apply this, this framework to a particular problem, which is if we have some kind of static features, we want to now predict a possibly multi-dimensional trajectory. And a common place where this problem can be found is like in pharmacology, where you might have some patient covariates like age, weight of the patient, maybe some biomarkers, and given those and a dose of the drug, you want to predict a drug concentration curve over time. And now the main difference between direct semantic modeling and all the other approaches is how the trajectory is actually generated from the features. So instead of just taking our static features and predicting the trajectory, in our model, we have something that's called a semantic predictor first, which takes those static features and then predicts something that we call a semantic representation of a trajectory, which describes its behavior. And this may be things like the overall shape of the trajectory, to which we refer as composition here, some transition points, so things like minima, maxima, inflection points, a few derivatives from for technical reasons, and some kind of properties of the long-term behavior. So that might be a horizontal asymptote, it may be the rate of decay, these kinds of things that allows you to predict into the long-term future. And then all of this is taken into a different model, which is not trainable, that we call trajectory predictor, that takes all of this and predicts the actual trajectory. So then the actual model that we propose, we call it episode, and it works in 3 steps. So first, we're gonna predict the general shape of a trajectory. And to do that, we want to do it interpretably. So we're going to use the decision tree. And this decision tree is going to take those static features, so in this case, for instance, those of the drug, and predict what kind of shape it has. Is it an increasing trajectory? Is it a decaying trajectory? Maybe first decreasing, then increasing. Then the second step is to predict all of those different properties, so minima, maxima, and so on. And to do that also in an interpretable way, we're going to use something called generalized additive models. And these are like very common interpretable models where the target value is the sum of univariate functions called shape functions, where each of them takes a different variable as input. So they are very nice because you can understand the impact of each of the variables on, for instance, the maximum of a trajectory, the minimum trajectory, and so on. So those models give you this semantic representation of trajectory, which basically looks like this. So this is like a kind of small symbolic representation. And finally, we have this trajectory predictor that takes all of this and predicts the actual trajectory. So this is how the model works. And then we performed a small case study on a real pharmacological data set to show what are the advantages of this kind of modeling. And this is going to be about incorporating prior knowledge, understanding the behavior of the system, verifying constraints, editing the model, and finally, flexibility. So let's start with incorporating prior knowledge. So let's say that one kind of prior knowledge that we would like to incorporate in our model is actually that the shape of a drug concentration curve over time is going to decay at the end. So this is kind of what we assume if we don't provide additional doses of the drug. We kind of assume that it should decay to 0 in the long run. So now the kind of prior knowledge that we can put into the system is that we're going to not allow any kind of trajectory shapes that do not have this behavior. So if it's just an increasing trajectory, if it just like goes exponentially down, we're going to disregard all of those. Instead, allow for only shapes that satisfy our kind of criterion, our prior knowledge. And there are two advantages of that. One is that we are guaranteed now that our trajectory is always going to follow one of those shapes. So if this is an important requirement, we don't have to worry about it. But also importantly, we reduce the search space. So now if we are in scarce data regimes, then the performance also is improved. Another important thing is this understanding that I mentioned at the beginning. So here we don't have to perform any kind of analysis, mathematical analysis, to learn about those like semantic representations of the model about this behavior. So we can just look at the decision tree that we trained. In this case, it turned out to be a very simple decision tree, which basically predicts that for all possible samples, the shape of a trajectory is going to be the same. It's going to be to this shape that like first increases, achieves a kind of maximum, and then decreases, and finally has this convex decreasing shape that approaches some kind of horizontal asymptote. And what's nice about it is that this is exactly what's going to happen in every possible case for every possible input. And then if we want to understand some other properties, like those like minima, maxima, the only thing we have to do is like take those generalized additive models we trained and look, for instance, how weight of the patient or the age of the patient is impacting the maximum concentration of the drug. Next important thing that we can do is verifying constraints. So imagine that in this pharmacological example still, one kind of constraint we would like to put into our model is to make sure that the trajectory decays actually to 0, right? So we don't want it to decay to a negative number or to like high positive number. It should, to make it biologically plausible and like a real model, it should decay to 0. And now it is very easy to verify this constraint. We can just look at the generalized additive model we trained, and we can see that in this example, it's actually not close to 0 at all, right? So we can easily see that this constraint is not verified, but we don't have to be like super upset because we can also edit the model. And that's a very important property. So in this case, we can now retrain our model and add an additional penalty term exactly on the value of the horizontal asymptote. And after the retraining, it turns out that now the value is much closer to 0, but we can go even a step further and manually set it all to 0, because the model is actually defined by all those generalized additive models, right? So this is not an explanation. This is actually how the model is defined, so we can set it to 0 and make sure that this is actually going to be reflected in every trajectory. And finally, flexibility. So because now we're not constrained to models being exactly in a compact symbolic form, we have a lot of more flexibility. And when we compare it to other methods discovered automatically or even expertly designed models, it turns out that our approach achieves better performance, and actually in this case slightly better even than black box approaches, possibly because like of improved like better inductive biases, smoothness, and this kinds of things. And we also tested it on like other real synthetic and real data sets compared with different ODE discovery methods and black box approaches. And in most cases, it performs better than those closed form expressions and has a performance comparable to those black box things. Yeah, so just to summarize, in the model, we use a decision tree to predict the shape of a trajectory. We use generalized additive models to predict different properties of it. We had to design a novel training algorithm for this kind of structure. And finally, presented case study where we showed the advantages of this modeling approach and flexibility in multiple experiments. And yes, well, thank you.
Okay, thank you very much to Krzysztof for that very interesting talk. Unfortunately, we ran over by a minute or so. And to be fair to Marta, who also didn't have questions asked to her because she ran over, I will ask you please to find Krzysztof in the coffee break and ask any questions that you have. But please do join me in giving all of our speakers another round of applause. And so yeah, it's coffee break, and we'll be back again at 4.
I hope you've been enjoying things so far, and I'm looking forward to having Eleonora talk to us about being right for the right reasons, which is very important. Over to you.
Well, thank you very much. So I'm Eleonora. I'm actually one of the assistant professors here in Imperial X. And well, this work, I've not done it on my own, obviously. It's done with Luca over here. Back then he was in Rome, and now I convinced him to come join my group. So I'm very happy about that. So as you can see from the title, we wanted to make neurosymbolic AI work a bit better. Now, there is a big debate on what is even neurosymbolic AI. What does it mean? I don't want to enter into that entire debate for the scope of this talk. So in this talk, for us, neurosymbolic AI will be something like this. We will have a neural network, and then we will have some symbolic knowledge, okay, that tells us, for example, that shark is a fish, that dog is a mammal, cat is a mammal, and so on and so forth. And essentially, we want to inform the neural network about this background knowledge, okay? Now, how do you do this? There are many methods to do this, and if you believe that shark implies fish in propositional logic can be rewritten as not shark or fish, then it can be easy to see that you can train your neural network to follow a loss like this one. How do you obtain this loss? Well, it's very easy. So you start with not, and you transform a not with 1 minus, okay? Then you take the OR, and the OR becomes a maximum, and the AND becomes a minimum, okay? If you ask why exactly these operators, it's because essentially, if you think about it, all of these operators, when you are working with values that are 0 and 1s, behave exactly like the propositional logic operator, right? 1 minus behaves exactly like the negation. However, the good bit about these operators is that they are differentiable, well, at least according to PyTorch. So we can actually define a loss and minimize it, right? So in this very simple setting, we have a neural network, we have some symbolic knowledge, which we compile into a loss function, which then we use to train our network. Now, I like to work with examples. So what would actually look like when we have this background knowledge? Well, we would have a neural network, something like this, with 7 outputs. And then we would have 1 output for shark, dog, duck, and cat. And then we would have 1 output for each of the superclasses, right? So we would have 1 output for mammal, 1 for fish, and 1 for bird. In addition, in our setting, we suppose that these, our final labels, are fully supervised, okay? And while these are either unsupervised or very weakly supervised. Okay, so we have some intermediate concepts for which we have very weak supervision, like 1 or 2 labeled images, and we have some final labels which are fully supervised. Now, one good question could be, like, why are we even interested in this problem setting? Well, if you think about, for example, fine-grained image classification, you can think that you can have a knowledge of some hierarchy, like, I don't know, this species of a duck is a duck that is a bird. And it's very, very easy to get, annotations that something is a bird, that is a mammal, and so on and so forth. But it's very, very costly to get annotation of exactly which species of a duck an image is, right? So it happens quite often that it's very easy to get these high-level ground truth annotations, but it's much, much more costly to get these fine-grained annotations. But it's also very easy to get access to this background knowledge. So this is the setting we are interested in. Now, what is the problem? The problem is reasoning shortcuts. What does this mean? Well, suppose you have a duck image, which is labeled with bird. Now, if our neural network is able to learn our fully supervised labels perfectly, okay? And it simply learns to put all the outputs for all the intermediate concepts equal to 0, we would get our loss is always equal to 1. So we would actually achieve perfect satisfaction of the constraints. We would actually get to a global optima of our loss function, but we have learned nothing, right? And this could be repeated for anything. So we could have a cat that is ground truth, whose ground truth is mammal. We could still have all zeros, and our loss would still be 1, and so on and so forth. So what is a reasoning shortcut? Well, a reasoning shortcut is nothing else than a situation where you have a neurosymbolic model like this that is managing to learn how to achieve a global optima of your loss function, but is not actually learning the semantics of your intermediate concepts, okay? It's literally learning a shortcut. It's being very lazy, okay? So what is the solution? Well, the solution is incredibly simple from a intuitive perspective, which is we needed to anchor in some way these intermediate concepts. So we need to give the neural network an idea that they cannot just try to satisfy this knowledge, but it also needs to learn that this dog is similar to this, and this duck is more similar to this than to a cat, right? And how do we do this? We can simply use prototypical networks. So in our setting, we suppose that we have one labeled image or one labeled data point for every intermediate concept. In the paper, we drop this assumption, but we don't want to go over that right now. And what does our prototypical network do? Well, our prototypical network essentially extracts an embedding for each one of our labeled images, okay? This essentially allows us to divide our embedding space, right? Then, given a new image, this image will be plotted in the same embedding space, right? Then what can we do? We can do something very similar to K and N. We can simply compute the distances to each one of the known embeddings or the known centroids. And this induces a distribution, right? Which is simply a softmax over the distances, okay? And then what we can do is simply use our semantic loss or our neurosymbolic AI model and train it over this embedding space, okay? Now, what is one of the results of the paper, or the most general result of the paper? Well, the most general result of the paper is the fact that when we do the update of our neurosymbolic loss, so our loss that is defined by the constraints, this is the gradient that we get. How to read this? Well, if you allow me some slack over the notation, this will be in our setting the set of shark, dog, cat, and duck. Okay, so our gradient is looking at the sum over all of our intermediate concepts. And then what is looking at? Is looking at how well we are satisfying our constraints. And also, if you look at it, we are looking at how close our embedding for our data point is to each one of the centroid. Why? Because this is the final output, which is the softmax. And this is literally a weighted average over all the centroids. So we call this the center of belief of our model. And then we are taking a weighted average over the distances, right? So even though this loss, as we have seen before, is simply based on the constraints, when we are doing the update, since the embedding are computed this way and the softmax is literally induced over the distances, by the distances over the centroids, then we get that the gradient also depends on the distance of the centroids. Okay? So this allows us to anchor each one of these images to a known prototype or a known centroid. Okay? And this allows us not just say how much we are satisfying the constraints, but it allows us to say not only we want to satisfy the constraints, but we want to put each image as close as possible to the centroids of those labeled images that we know. Okay? So how does this work? Like, does it actually work with very simple intuition? And again, very big fan of very simple data sets. So actually, this is simple data sets for the type of images you deal with, but it's very complex for the reasoning shortcut perspective. Why? Because in this data set, you are only allowed these pairs. So you are allowed different 0s and 6s, so you can have different images, but they all will only appear in this pair, okay? So we will only see a 6 in conjunction with a 0 and with a 4, okay? And this pair, which we are given an input to our prototypical network, is labeled with their sum, okay? So imagine you have a network, it's taking an input to images, and the only known ground truth is their sum, and you have to learn it. You have to learn these intermediate concepts. But you have not access to all the possible pairs. You have only access to these 8 pairs, right? So for example, you could swap 0 and 1, 6 and 5, and you would still perfectly satisfy your constraints, okay? Now, if we have a look at how we do with respect to all the other mitigation strategies that have been proposed so far, I think we do a pretty good job, especially if we look at how our PNet does with respect to each one of the mitigation strategies take in isolation. So here we have 3 how to read this table. You have 3 new very standard neurosymbolic methods. I put the citations below. You have the problog, semantic loss, logic tensor network. And the 2 metrics I plotted here are the F1 score over the intermediate concepts and the concept collapse, which is an idea of how much your network is collapsing the intermediate concepts. And here, on top, plus R, plus H, plus C, are 3 different mitigation strategies that have been proposed in this 2023 NeurIPS paper, used in conjunction with each one of these methods. And as you can see, the best model, I think, can only achieve 55% F1 score, while by simply using a PNet, you can achieve a 98%. So even though the idea is extremely easy, at least in this benchmark, we managed to get much better results. Now, also to give you an idea of what, to give a visualization of the results, here there is what the standard semantic loss would do. So as you can see, what it does is mapping a lot of the digits to either the digit 3, the digit 4, or the digit 6. Here, what we have done is we have said, OK, we know what will help you a bit. So we labeled actually 200 images, and we pre-trained the network first with that, and then we trained it to satisfy our background knowledge. And as you can see, we are able to kind of recover the diagonal a bit, but not really. And then here, we have just 1 labeled image for each one of the digits, and we are able to perfectly recover the diagonal. So also to show you how the decision boundaries evolve during training, this is the standard semantic loss. And what we have done here is essentially done a PCA over the logits. And here you have the dots that are colored with their actual digits, so the ground truth digits. And here are the decision boundaries assigned by the neural network. So here we can see again that in this run, standard semantic loss converges to assigning, I think, mostly 4, 0, 6, and 3. While, as you can see, if you use semantic loss with the prototypical network, you're actually putting the dots colored in the yellow region, and so on and so forth. And as you can see, we are able to actually fragment and differentiate among the intermediate concepts. Another big bonus is the fact that if you use these standard neurosymbolic methods with different level of unsupervised data points, well, you can get a lot of noise. So here what we have done, we have actually trained each one of these neurosymbolic AI models. We have actually pre-trained them with the famous 200 labeled data points. And then we have also added concept supervision. So we have labeled all images belonging to 2 classes, namely 4 and 7. Okay, so we have given it a lot of advantage. And as you can see, it's not like if you add more unsupervised data, you're getting better results. Actually, it gets very, very noisy. While if you simply do what we were saying, just label one image for each one of the digits, you get robustness with respect to the amount of unsupervised data points you add. So as you can see, you get very nice lines, and it's also, sorry, a bit of noise. It's also very, very stable. So finally, so far one can say we have only talked about mixed addition. Is it really an interesting task? We have also tried this on an autonomous driving task, in particular on this data set that is called BDD OYA, where essentially this is a data set where you have a bunch of images, and the only ground truth label that you're given is the action that the car is taking. Okay? So the car is either moving forward, stopping, turning left, or turning right. And the intermediate concept that you have to learn is the reason why the car is taking those decisions. So did it stop, for example, here because it saw a red light or because there was a pedestrian? Okay? And you have also available this background knowledge, which tells you like that red light implies no green light, and that, for example, if there is a green light, or if you're following another car, or if a road is clear, then the car should move forward. Okay? And again, this is a very complex task, so obviously we no longer get the very nice 98% F1 score, but you can see that if you look at the standard deep problem, then it only manages to get 8% in F1 score over the concepts, with an 82% of concept collapse. If you train the same deep problem with the pre-training, so again here we have labeled 200 images, actually it's doing worse. So it's losing a bit on the intermediate concepts, and it's even doing a bit worse in concept collapse. Now here it's not shown, but it's probably doing a bit better on the final labels, so on these labels over here, over the action. If you simply take deep problem plus our PNet, suddenly you get 16% F1 score, not great, but it's a 10% jump, and 35% concept collapse. So even in a task like this, which is very messy and not as nicely framed as mixed addition, you can get quite a big jump by simply using prototypical networks. So I think I am done. Here there is the QR code to the GitHub repo that Luca has implemented. There are a lot of examples, and it should be quite easy to use. If it's not, please email us. And do you have any questions? Thank you very much.
Questions? I can give people a bit of time. One of the things that I was thinking about was just to sort of think about the kind of wider set of tasks where you have this logical side information. So I'm sure you have this very fluent. So what are the kind of canonical use cases that people turn to when applying this, and how long a set of sort of logical accompaniments is it common to have?
So it depends. For example, if you look at hierarchies, a very common task is protein function prediction. So where you have 3,000 classes, something like that, and you can have hierarchies with like up to 13 levels. So actually a lot of these constraints, very simple constraints, but quite a lot. For example, we have worked a lot on tabular data generation, where you have normally, companies that want to generate tabular data, but then they are not really compliant with their background knowledge. So you want to add this additional knowledge. In autonomous driving, because it's a safety critical task, you normally have constraints like if there is a pedestrian, you should stop, or traffic lights shouldn't be red and green at the same time. In general, in tabular classification, you can have any relationship between the inputs and the outputs. So I don't know, if a patient has the blood pressure above a certain amount, then he shouldn't take this medication, things like this. So there are a lot of tasks where you have constraints. It's not so common to have them codified.
Right. Other questions from the room? People are beginning to feel the burn. Okay, that's very good. Well, while you were talking, I'm going to abuse maybe my chair's privilege. So obviously you were talking about a setting where we have a declared set of logical constraints. Is there any advantage to having a sort of a model which acknowledges that there might be latent and unobserved logical constraints? So you say, I know that there are additional logical conditions. I don't know what they are, but there exists some other hierarchy in my data set. So do people do that?
I mean, in a sense, it's what we are trying to do in machine learning, right? You're trying to learn some sort of correlation or some pattern in your data.
But it would be like latent symbolic, right? So
there is an entire branch on constraints elicitation or a constraints extraction from the data. It is called inductive logic programming, for example. But yeah, it's a completely different set of tasks.
It's not helpful to bring the two together, because you might imagine a kind of probabilistic relaxation of what you're doing, or which you observe some constraints.
I mean, that's actually what they were trying to do in the 80s. So before neural networks were even a thing, people were trying to essentially they had a lot of systems that, for example, were classifying your spam, that were rule-based. So they were writing all the rules, and then they were perturbing them literally in a neural network.
Right.
And to learn additional rules. So they had these hybrid systems. Now I think it's a bit more difficult, but yeah, there is an entire field to explore that is very much underexplored.
Right. Assuming we don't have any more from people in the room. So is Peter here? I think Peter has had some kind of event on his way to join us, which is perhaps good news for people, because maybe people are flagging. There's one slide. How do I advance? Is it on this machine? So there's a slide from Georgia. A link. There's a QR code slide that came from Georgia. Got it? Neat. Okay. So Peter probably sent his apologies. Georgia definitely does. So if you had done the arithmetic, you'll have already worked out we only had time for 2 people to talk in this slot. And that's because Georgia has kindly can't make it because she's in the wrong country. And we wanted this to be an in-person event. But she has pre-recorded her talk for you, and you must click on this link as soon as you can, because I think it expires by Friday. So be quick on the draw. Right, in which case I'm going to wrap things up. So of course the people that I should thank are the speakers for giving us a really fascinating set of previews of NeurIPS and post-views of ICML. It's really appreciated. Yeah. The clapping key. I also really want to thank Andreas Jürgensen, because he helped collate this event academically for you guys. So if you found it stimulating, you have him to thank. And also particularly call out Lauren Burton, who ran a lot of the process side of this event, which is very successful. And then they both were supported by our excellent team of Eileen Boyce, Hannah Matthews, and Tracy Busselli. So can we give a big round of applause to people for organising things? And this would, of course, be impossible without the support of Schmidt Sciences, so thank you very much to them as well. So we've changed this event. In the past, we kind of focused on having a sort of small number of long talks that kind of gave more of a kind of overview style of things. But we found that the speakers, A, didn't get down to the nitty-gritty, and B, just talked about their own stuff instead of giving people a good overview. So we've taken a different approach and sort of tried to bring a lot of diversity in with fairly high density. So, you know, through the various channels, give us feedback about how you found the day. I certainly enjoyed and appreciated everyone's talk. So with that, thank you, everybody, and until next time. Cheers.